E2, which is just the orthogonal projection on the first Hermite functions. So it's given by sigma, because of their, as they were real functions, sigma of phi n of E1 times phi n of E2. Okay, from 1 to 10, from 0 to -1, because they are labeled from 0 to -1. And what we saw last time was that for the correct spacing near the origin of the EJs, so there is a rescaling if you want, and the correct formulations to write, for instance, E1 is equal to pi over square root of 2n times x1, and similarly E2 equals pi over square root of 2n times x2. Then what we saw is that kn of x1, x2, of E1 into was in fact equivalent for n going to infinity. It was equivalent to the square root of 2n over pi times sine of phi x1 minus x2 over pi times x1 minus. And that knowledge, I mean the knowledge of this behavior of kn, was sufficient to and this is final on the correlations. What you want is determine this. Of course, it's E of ns ds. Now, there are obvious things which are true. For instance, if we look at the probability that there is no eigenvalue, which is E of 0s, this function is certainly going to be 1 for s equals 0, and it's going to decrease with s. Okay? So the E of 0s will have artistically the following shape. And then we shall have E of 1s, which is the probability that this interval of length x, because I mean the rescale, so that this is the average density, so you should take it to 1, the rescale is 4. So if you take E of 1s now, I mean this is going to start from 0, and it's going to look like that. And in general, I mean E of ns will be something which looks like this. Okay? The rule, however, which should be obvious, is that the sum from n equals 0 to infinity of E of ns would be equal to 1. Okay, because I mean, if you take an number of length x, I mean, there is a total probability of 1. Okay, some number of x. Okay, so let's determine this. We have all the tools to do it. And in fact, I mean, I will do the full computation only for n equals 0, so other computations are the same. Okay, so let's take let n equals 0. Okay, so what we have to do simply is to compute the probability that there is 0 eigenvalue in the interval of this length. So what does it mean? It means that we simply have to compute the integral where each eigenvalue is bigger than, well, let me call theta equals alpha t. So theta is equal to square root to pi over square root of 2 times t. Okay, so what we want to integrate for all ej bigger than theta. of Pn of E1 in the up to Pn, E1 up to Pn. Okay? It's clearly what we need to compute. Now what is this? This is given by the determinant square, which so many times how we should handle this. And so, I mean, I remind you, it's given by 1 over n factorial. Did I write this somewhere? Yeah. Okay, so it's given by 1 over n factorial. And then we shall have a sum. There will be epsilon of sigma. There will be epsilon of phi. And then we shall have terms of the form phi of sigma of 1 of E1, phi of 1 of E1, and so on. All right. So I mean, when we compute, since this condition is perfectly symmetrical, Ej is bigger than for all j, what we shall find is that we can suppress the 1 over n factorial, and we can suppress one of the summation in the permutations. And so what we get is the following. We get a sum. There is no longer 1 over n factorial. There is just a summation over one permutation, which we want to choose. And then we have certainly the signature of permutation, sigma. All right, and then we have to take these integrals where the same variable enters, but we only have to take it from Ej bigger than beta. Okay, so typically what it would give us, it would give us a product, because this integral of course separate. Okay, the product from 1 to n, okay, of what? So the first one will be phi 1 multiplied by, see what I will denote by 1 minus p sub theta times phi of sigma of 1. Okay, and then there will be phi 2 times 1 minus p theta phi sigma of 2 and so on and so forth. Okay, and so I should write generally if you want the notation, and we just write phi, the product of phi j, sigma of j. Yeah? Okay, so it's a product from 1 to n. Now, 0 to n and so on. Okay. Now, what is this p theta? Okay. Well, this p theta is just a truncation to the variable being less than theta. In other words, p theta is the multiplication of the header in L2 of R, okay, by the function which is the characteristic function of the interval minus theta. Okay, and it's obvious that if I multiply by 1 minus p theta, it is the same thing as restricting integration for the values of the integration variable, which is bigger than theta. Okay, so what is this sum? It's obviously a determinant, okay, but a single determinant, not a square. So in fact, this probability is equal to the determinant of what? Of Kn. Remember that Kn was the orthogonal projection of the linear span of the phi j's. Okay, we are in an n-dimensional space. Kn times 1 minus p theta times Kn. And what do I mean by this? This determinant is taken in the range of Kn. Right? So you see, we are in an n-dimensional space, okay? And I mean, this is obviously the determinant of this matrix in the basis given by the phi j's. And so, I mean, we can also write it as a product from 1 to n of 1 minus the eigenvalues lambda j n. Okay, well, I mean, I put n here also that you don't have to use an exponent. But what are the lambda j n? Well, you see, Kn here, if I use a 1, I mean, it's just the identity because I am in this subspace. Now, the other thing is what? It is Kn times p theta times Kn. But whether I put this Kn or not doesn't make any difference. Okay, so in fact, I will look at the following eigenvalue problem. So, whose solutions are the lambda j n. So the eigenvalue problem is the following. It is, you look for functions psi which satisfy the condition that if I take Kn of p theta and I apply this to psi, okay, I should get lambda times psi. All right? And I mean, of course, I don't want with lambda different from 0. Okay? If I take lambda different from 0, the function psi necessarily belongs to the range of kn. Okay? Because of this equality. And I can reinsert the kn on the right-hand side if I wish, because the function is in the range of kn. Okay, so this equation is correct. All right, so to understand the behavior of these quantities then, okay, so what do we know? We know that for finite n, we have that E of 0s, okay, E of 0s, but with a subscript n, which means that we didn't yet take the unified one in the Riemann. Okay, it's given simply by the product of the 1 minus lambda jn. Of course, this lambda jn do depend on whatever variables are around, the theta. Okay, so to understand what these numbers are, what we have to do now is to let n go to infinity and to understand what is the limiting equation of this equation when n goes to infinity. Okay, that's clearly the case. So what will it be? I don't want to erase here. What can I do? Or maybe I can just erase it. Okay, so what is this equation looking like? Okay, so remember that Kn was given by a kernel, an integral kernel, so we can write the equation for the lambdas like this, that integral of Kn of E1 and E2, okay? And then I put P theta of psi of E2. Okay, I'm just, it's not this rewriting. E2 is equal to lambda times psi of E1. Okay, but you see, putting P theta in psi of E2 here is the same thing as integrating for E2 less than theta. And this is equal to the same as integral for E2 less than theta of Kn of E1 E2 psi of E2. Okay, so now the number theta should be exactly as it was here. Okay, it should be rescaled with density, namely pi over square root of 2n, so that the number that we have here is in fact pi over square root of 2n times t. Okay. And when we look at this equation, we can rescale the variable in the function psi, okay, and also, of course, in the function kn, because we know exactly the behavior of kn. To know this behavior, we just have to replace E1 by pi over square root of 2n x 1. Okay, now, what will it give? So let me just rewrite what this equation gives. When we put E1 equals pi over square root of 2n times x1, and theta equals pi over square root of 2n t. So what does it give? It will give integral of, so I take the limit of kn, so it is square root of 2n over pi times sine by x2 minus x1. Okay, over pi x2 minus x1. And then what do I have? I have psi. Let me put up psi theta because I have changed variables. I want to look at the function of x. So psi theta of x2. Okay, and it's for x2 less than t. Okay, and then I have dE2, but the dE2 is exactly pi over square root of 2n times dx2. Okay, so this term cancels with this one. Okay, so I get and then we have the lambda now. Lambda j no longer n because I have taken n to infinity. Lambda j times psi theta. All right, so what do we get? We get the following result that right here. Okay, so as I said, I mean, this result is a standard result of random matrix theory. But I mean, the very nice fact is that it will involve exactly the same objects as we had here from the spectral organization. So what do we see? See, we see that the first function, p of 0s, is equal to the product from 1 to infinity of 1 minus lambda j of s, okay, where the lambda j of s are the eigenvalues of the eigenvalues of what? You see what happens here now. What happens here is that we have an operator on the left that is denoted by t. So this equation is like t psi theta is equal to lambda j psi theta. What is t? T, what do? I first truncate the function psi theta, so I multiply it by p sub t. And then I make its convolution by this kernel. Okay? Now what I claim is that convolution by this kernel is exactly the Fourier transform of the projection p sub pi. Okay, so you know what the statement is the following. Whereas again, the value of the operator, I will make it self-conjoint, of the operator, let us first write p sub pi, and I put Fourier here, times p sub t. Okay, so let me make the notations more precise. Okay, where p sub t, I mean, where, or p lambda, if you want, for any value of lambda, is the multiplication operator by the characteristic function 1 of the interval minus lambda lambda. This is true for any lambda. Okay, and p lambda at, I put a hat here, is just the conjugate of p lambda by the standard Fourier transform, where Fourier is a standard Fourier transform where the basic character of the real line is taken to be the exponential. Standard Fourier transform with basic character alpha of x equals the exponential of ix. Okay, so what do I mean by this? I mean that the Fourier transform of a function, okay, Fourier of psi, evaluated at u, is just given by the integral of exponential I x u times psi of u du. Alright. Now, if you compute what is the Fourier transform of the characteristic function of the interval minus pi pi, okay, I mean, you see obviously that this Fourier transform is such that when you multiply it by the variable, it means that you are differentiating this characteristic function. So you get the sum of two delta functions. Okay? Now there is a discrepancy by 2 pi. You see, because normally if I have twice the exponential here, I will get something like exponential of I pi x. Okay? And because there is a minus, because on the other side you have minus exponential of minus I pi x. Okay? So you are missing the 2 pi. Okay? Because normally you have 2 pi. Okay? But the 2 pi is coming from the torsional function. Okay? So I mean it's on the nose. The 2 pi is exactly because you invert when you write convolution. You invert it. So it's fine. So it's exactly given by this, the eigenvalues of this operator. And I mean the second statement, which I won't prove because I would waste time doing it, but I leave it to you as an exercise. So please check the following without looking at books. E of ns now. Okay, the probability is that you get exactly n eigenvalues in the interval of length x, or if you want, symmetry is 2t, 1t on each side. E of ns is in fact given by the Taylor. Is given by the Taylor expansion. By the Taylor expansion. At z equals 1 of the function f of f sub s of z, which is the product of 1 minus z times lambda j of s. Okay? So So in other words, when I say it is a Taylor expansion, what I mean by this is that f sub s, more precisely, f sub s of 1 minus z, I have to put a minus sign, should be equal to sigma from n equals 0 to infinity of e of ns times z to the n. Okay, and I mean, for instance, you can check immediately that, as I said before, the total probability has to be 1. So the sum of z of ns has to be equal to 1. Where does it come from? Well, you see, if I take z equals 1 here, I am just taking the determinant of 1 minus 0. Okay? And of course, this is equal to 1. And you can check the those. Now, as I said, much later, probably in the last lectures, we shall have to study the pair of projections, which is given by truncation on an interval of length lambda, or 2 lambda, and its Fourier transform. And I mean, what happens is that, in fact, the behavior of this pair of projections only depends on the product of the arguments. So here, it only depends on the product by t. And what I'm saying simply is that, you see, already in the theory of random matrices, this pair of projections occurs. And it occurs completely because, of course, you see, when you know these functions, u of ns, in fact, you completely know the list of eigenvalues of these pair of projections for each value of s. Now, it turns out that in a random matrix theory, it's more like the small values of s which are relevant, because one needs to look at the statistics near the origin. Okay? Whereas what we shall see much later, it will be the very large values of the parameter. But still, I mean, I find it very sort of provoking, if you want, that you have exactly the same pair of projections and the same eigenvalues. And by the way, I mean, the eigenfunctions are these Rolle's spheroidal wave functions. Okay, so that would be it for random matrices. And so, I mean, I spoke about them for essentially for 2 reasons. I mean, the first one that was the empirical evidence that when you look at the zero projections, they do behave like the eigenvalues of a random Hermitian matrix. Okay? And then a few non-empirical facts. And the second reason, which was, I think, hopefully more important, is this much more precise connection, where, in fact, by looking at, not at the correlation functions, but by this probability, or having a given number of eigenvalues in an interval, you find, in fact, exactly the analysis of this pair of projection. Okay? Okay, so that's so far as I will go for random matrices. So what I want to do, I have given in the first talk a detailed motivation, if you want, from a sort of standard material of why the approach by quantum chaos cannot work, just because of this overall minus sign. Why it's indicating that the spectral interpretation should be as an absorption spectrum. That was very important. And I mean, why somehow, if you want, when you want to bypass this big problem of the minus sign, which was given by the theory of quantum chaos, there was a need, an absolute need for getting enough variability in the problem that somehow you can specialize it to another case and understand what happens. Okay? And this variability was given by global fields. So what I want to do today, is state the preliminary result on spectral interpretation. In fact, I will state it several times, doesn't matter. Okay, but as I say, it's a preliminary result because it uses still this exponent, which will be removed later. But mainly, what I want to do is to show you where it came from and explain somehow, in what sense, the local class field theory, which is sort of so interesting and rich for non-Archimedean places, as a substitute at the Archimedean place, okay, and which is behind the spectral realization of general theory. So that will be, I mean, I will first state the theorem in the framework of global fields, And then I will explain a lot of things which are behind it. But, I mean, somehow if you don't know these things, then it's not so good because, I mean, you know, it's like stating the result, you do not know where it's coming from. So I really want to do that. Even though you could consider it as a parenthesis. Oh, it was silent. It was precisely the time when it should turn off. Okay, so then let me explain this. So, you see, first I want to present the spectral interpretation in terms of okay, is what is a global field? So a global field K. So of course it should be a field, okay, as the name indicates.
It should be global.
And now it should be global. Okay, so what is it? I mean, so okay, it's a field K commutative, which is sitting inside a locally compact K is discrete, a locally compact ring, and this locally compact ring should be non-discrete, non-compact. Non-compact, I mean, if it were compact, the field would be finite. But it should be semi-simple to avoid some rather uninteresting situations. Okay. And moreover, I mean, it should be inside in such a way that it's almost the same thing. Namely, so that it is co-compact. And discrete, of course. Okay, now, saying that this ring A is semi-simple, what it means, if you want, in particular, is that the intersection of the maximal ideals is equal to 0. And when we divide A by such a maximal ideal, what we obtain is a locally compact field Now, these locally compact fields are known. We have their complete list. And I will come back to that later. But such maximal ideal and locally is called a place of K. Okay, and the completion, if you want, for the place, namely this quotient, is called K sub V, and it's a local field. All right. Okay, so before I come to, if you want, distinction between Archimedean, non-Archimedean, and so on, and explain, let me just state the result. So the result about the spectral interpretation is the following, is that you see if you have a global field like this, a lot of things emerge just from A. So in particular from A, what you get is a group which is GL1 of A. GL1 is an algebraic group, so you can apply it to A. So you have GL1 of A divided by GL1 of K. Okay, that's a group C sub K, which plays a very important role in number theory, and which is called the ideal class group. Now, the ideal class group is a group which is essentially commensurable to the positive real numbers by something which is called a module, which goes to positive real numbers, and which is simply obtained by letting GL1, not GL1 over the quotient, of course, but GL1 act on A and see how the R measure is modified. So if you take D of Gx, where J is in GL1 of A, and X is an element of A, I mean, this has to be given by a multiple of the R measure, by unicity of the R measure, where dx is the additive R measure on A, and this is called the module. Now, the map, which is the module, makes the ideal class group commensurable with R plus star, and I mean, the global fields fall into two classes. there is one class which, as I explained first time, has a very well understood geometric significance, which is the case where the characteristic of K is positive. And in that case, the module, namely the range, okay, of the map, which is the absolute value, is in fact formed of powers of the number of elements of the largest finite field, which is in K, okay, which is a finite field, so that Q is a power of a prime, P to the L. And okay, as I said, everything is fairly well understood there. And the other case, in that case, if you want, the range is Q to the power Z. But so what you have is you have that this ideal class group maps by the module to Q to the Z. And it has a kernel, of course. This kernel is called, let us call it CK1, elements of modulus 1, if you want. And this CK1 is in fact equal to the Galois group of the maximal abelian extension of K over the maximal unramified extension of K. Okay, so let me denote it by this. And powers of Q can be interpreted through class field theory as not the full Galois group of the unramified extension over K, but as a dense subgroup. Okay, so which is called, when you assemble the two, this is called the Veil group, and the fact that it is isomorphic to the ideal class group is the content of class field theory for that. Okay, now if you look at the case of characteristic 0, so if the characteristic of K is equal to 0, then the range of the module is equal to R plus star, and the field is necessarily a number field, so K is a field of algebraic numbers, so it's a number field. And but apart from that, the two situations are fairly analogous. Now, we can again, in that case, write CK, you see, contains a subgroup CK1, so CK maps to R plus star, surjectively. And we have CK1, which is the kernel of the module. And CK1 is, in fact, the Galois group of the maximal abelian extension of K. If I take K to be the rational numbers, otherwise it's more delicate. You have to divide by the connected component of identity in the ideal class group. Okay, fine. But at that level of generality, of course, I will make much more refined statements later. What we see is that we have a nice locally compact group, CK, which is essentially commensurable to R plus star. Okay. And it's a modulated group. It has this proper homomorphism with co-compact range in R plus star. Okay. No, here there is no question of Frobenius, because if you want, here, no, not yet. I will talk later about it. All right. So now what I want to say simply is the following: is that the theorem, which I will prove not today but later, I will just comment about it today, is the following: is that if you look at the space X, which is a quotient now of A by GL1 of K. Okay, namely you consider the space of Adel classes. You see, at first, when you look at this space, it looks very innocent, because it looks you don't do very much something different from dividing, for instance, GL1 of A by GL1 of K. But as we shall see, this space is very elaborate space when you begin to look at it seriously. And now what we shall do, we shall simply take, you see, this space sort of contains the quotient of GL1 of A by GL1 of K, because GL1 of A is contained in A. Okay, GL1 of A is just a set of invertible elements in A, the set of ideals is contained in A. And so what happens is that if you take functions on X, you can restrict them to GL1 of A by GL1 of K, essentially. Okay? And the statement of the theorem is that the co-kernel
the co-kernel of this restriction map, of the restriction map, from L2, and there will be this decoration delta, which eventually will go L2 delta of x to L2 delta of ck. So delta, as I said, is like a Sobolev exponent. Okay, so the co-kernel of the restriction map is the Pauli Hilbert space.
Is there a problem with the topology on the no is not the topology coming from Adel?
Well, that's not a problem, but it's one of the sort of subtle features of the thing. Okay, I mean, it's of course extremely important. But at this level of generality, let me not enter into the details, because what I want is to give you some sort of a, we shall focus more and more on this space. At the moment, I just want you to remember that, you see, the spectral interpretation, which unfortunately at this stage will still have the delta, will be so simple that it will just be the comparison of the L2 functions on the Adel classes with their restriction to the Adel classes. That's how it will be. Namely the co-kernel. And when I write the co-kernel, of course, you see there's the sort of a characteristic feature of the absorption spectrum or of a cohomological description. Namely, I am dividing, if you want, it's like the negative. I am like taking a photographic negative of the space, because I am dividing by the space of functions on Adel classes. Okay? So this is our first acquaintance, let us say, with this spectral realization. Now, what I want to describe really is a lot of things which are behind. And so I will, knowing that, if you want, this is sort of our, intermediate campground, okay? What I will do, I will sort of go back to global fields, and please allow me to discuss global fields and local fields in general, and to explain to you why the local class field theory is deficient when we consider Archimedean places, and by why this deficiency is in fact replaced, okay? So let's go back to, let's erase this, and let's look at global fields. And you see, when you want to understand global fields, of course, the first thing that you need to understand are local fields. Because after all, as I said, a global field is something which is intimately related to a locally compact ring, which is semi-simple. And the maximal ideals of this semi-simple locally compact ring, when you divide by these maximal ideals, you obtain local fields, namely locally compact fields. Okay. Now, what are these fields? Well, essentially, they are analyzed, again, by the module. So it is the same sort of story, if you want. I mean, here I am just, at first, talking like André Weil in his book Basic Number Theory. So what you have is a module for a local field. So K is a locally compact field now. And what is the module? So the module comes from the action, if you want, x goes to lambda x of k cross the multiplicative group of k acting on the additive group on k. Okay. Now, again, we have R measure on the additive group k because it's a locally compact group. And we have that d of lambda x is equal to the module lambda times dx. This module doesn't depend on any normalization. Okay, it's uniquely defined. And so it's a map. So lambda belonging to k star, the invertible elements, goes to absolute of lambda, which is a positive real number. Okay. All right, so to analyze these locally compact fields, what one does simply is one looks at the function which is the module of n times 1. Sometimes when you want to refer to say that you are in a certain given field k, you use this subscript to indicate that you are inside k. Okay, of course, because if I would write n times 1, it doesn't look. So, I mean, n times 1, what you find is that there are two cases. And, I mean, essentially, you analyze a function which is a positive part of the log of n times 1. Okay? And you find that there are two cases. You find that always this function is given by a constant times log n, just by abstract nonsense. Okay? Just by writing down very simple inequalities. And then there are two cases, essentially. I mean, so log plus is a positive part of the log. So there are two situations. There is a situation where lambda is not 0, and there is a situation where lambda is equal to 0. So when lambda is not equal to 0, what you find out is that the module, which does define the additive topology of the field. Okay, it defines the basis of neighborhood of the origin. I mean, if you look at the things where modulus of x sub k is less than some number epsilon, if you want, this is the basis of neighborhood of 0. Of the origin. And so, I mean, what you find is that there are really two quite opposite situations. If lambda is different from 0, then what you get is that the topology on Q, that Q is injected, and that moreover, the closure of Q inside the field will be equal to the real line. Okay, and this is what one calls an Archimedean local field. And there are only two cases, which is the field is the real numbers or the complex numbers. Of course, if you take few fields, you also have the quaternions. Okay, now the other case is the case when, so this is when lambda is different from 0. Now, the other case is the case where lambda is equal to 0. And then what you have is that you have inside K, you have a subring R, which is in fact the maximal compact subring. Okay, and I mean, this subring is defined by the condition that norm of x sub k is smaller or equal to 1. Okay, R is a set of x satisfying this condition. And what you find out is that, I mean, if you divide, first of all, the module is discrete. So the module of k is a discrete subgroup of R plus star. In fact, it's powers of some number q. Okay, and moreover, if you divide just from topological considerations, and if you want, then R as a maximal compact, as a maximal ideal, which is compact, but okay, and when you divide R by this maximal ideal, R over, in fact, this maximal ideal is singly generated by pi. When you divide R by pi R, what you find is a finite field, FQ. Okay, so I mean, then there are two cases, essentially. There is a case when you can't lift FQ inside K. That's a case of finite extensions of p-adic numbers, of QP. And there is a case when you can lift FQ inside the field, which means that the field has non-zero characteristic. And then what you get is FQ of pi, namely formal power series over FQ. I mean, at this level of, I mean, it is quite important, of course, that you don't have to take algebraic extensions, because any algebraic extension of this local field is of the same form. Okay, and this is why you have really a geometric interpretation in the case of non-zero characteristic. All right, so now what about class field theory? See, so this was a description of the local fields. So now let me talk about extensions of local fields. You see, and let me talk about unramified extensions. So if one considers an extension K1 included in K2, where both are local fields, so just locally compact fields, then it does happen sometimes. I mean, of course, I don't want to consider the Archimedean case, because the only non-trivial extension like this is R included in C, which looks very simple. Well, it's a bad place to stop, but so let me say one more word. Okay, so I mean, this extension will be called unramified when, if one looks at the pi 1, if you want, which is a generator of the non-trivial ideal here, it is still the generator here of the non-trivial ideal. Okay, and I mean, this of course has a geometric origin, because it means that the uniformizing variable at this point doesn't change when you go to the cover. Okay, so we shall come back later. Okay, so as I explained, I mean, thing that I want to do now after just stating what is this spectral realization and polarized of space. Oh yes. So the next thing I want to do really is to show what's behind and why this space of Adel class is really a highly non-trivial space, even though it looks quite innocent. So you see, I want to review, I reviewed what are global fields and so on. I just want to review a little bit of class field theory to show you how class field theory is deficient for Archimedean places. Okay, so I mean, let's look at the local situation first. Local class field theory. And I mean, so precisely I will start with the local field K, which is not Archimedean. Okay, so if you start with such a field, then you can take a separable algebraic closure of K, and then what you have is you have the maximal unramified extension of K. So as I explained, you see the extension is unramified when this pi, which generates the maximal ideal of the maximal compact subring, is the same when you go to the extension. And what does it mean, such an ramified extension, say, of first of finite degree? So if you have a K included in K1, let us say, which is unramified, then what it means simply is that you have just extended the residue field. Okay, so if you had FQ, then what you have done is to adjoin to FQ some roots of unity of order prime to the characteristic of the residue field here. Okay, and that gives you the extension. Now, so the maximal unramified extension is really obtained by replacing the residue field FQ by its algebraic closure. This algebraic closure is just obtained by adjoining roots of unity, all roots of unity of order prime to the characteristic. And moreover, it has a beautiful Galois group. This Galois group is generated by the Frobenius transformation, which is such simply that Frobenius of x is equal to x to the power p. Okay? It is topologically generated by the Frobenius, but of course, I mean, it's a compact group, the Galois group. And it's very important that one uses this nuance in class field theory to topologize so that one only takes integral powers of the Frobenius. Okay? And this gives a Weil group. Now, containing this unramified maximal extension, there is the Abelian maximal extension of the original field, which is, if you want, the quotient of the Galois group by the commutator subgroup, and which is contained here. Okay. Now, a main result of local class field theory, of course, in the non-Archimedean case, is that one has canonical isomorphism between the local Weil group. So it's just a question of you want, of not taking the full Galois group of the maximal unramified extension, but only powers of the Frobenius. So this Weil group, local Weil group, is isomorphic to K cross, namely the multiplicative group of K. Okay, so that's for the local case. Right. Now you see, obviously there is a very big flaw, because if you take K to be R or C, okay, I mean, well, there is this sort of minute and trivial nuance between R and C, but I mean, if you take C, there is nothing apparently of interest which is going on. Because okay, there seems to be sort of nothing to classify or nothing to look at. Okay. Now, if you look at the global case, situation is very good when you consider a field which has only non-Archimedean places. Only if you consider a global field K of positive characteristic. So when the characteristic of K is positive, of course, all places will be non-Archimedean. And in that case, if you want, the beauty of the local class field theory will reflect in the global case that, in fact, you will have an isomorphism again of the Weil group, okay, which is obtained by retopologizing the Galois group, okay, with this nuance that I said, and it will be canonically isomorphic to the Idel class group CK, which is GL1 of the Adels divided by GL1 of K. But there is nothing like that when the characteristic is 0, And I think there is a paper by André Weil in Tohokuma's journal in 1947, in which he explicitly stresses, that this lack of existence of an interesting Galois theory for the Archimedean places is one of the main reasons why we don't have the replacement for the Frobenius and so on. So what I want to explain to you is that there is such a theory, okay, and that it is precisely that theory that led me to this Adel class space. Okay. So I don't want to do it in details because that's not the topic of the series of lectures, but I really want, though, to give you the main ingredients of this. Okay, so you see, what can we do which is non-trivial if we consider complex numbers? Okay, it seems that a priori there is nothing you can do because the field is algebraically closed. So it seems that you will be stuck. Okay, so let's take K equals complex numbers. All right. So as I said, you see, the full discussion of what is the Frobenius of this so on is a discussion where you handle modulated groups, namely groups which have a module. This goes to R plus star and so on, and this module is obtained by considerations of the R measure and so on and so forth. Okay. All right. So it turns out that there are objects, which are rather delicate objects, and which are tied up with complex numbers, and which have exactly these properties. And let me explain why, conceptually, they should arise. And so let me ask the following question, which looks a little bit crazy, and it is the following. Is C algebraically closed? Okay? So of course, it's a willingly provocative question. Okay, and of course, if you take the sort of naive definition of what is an algebraically closed field, there is no doubt it's algebraically closed. But let's try to make this definition a little more conceptual. Okay, so when should we say that a field is algebraically closed? What does it mean, really? It means that if we consider representation theory over K, over the field K, okay, the fact that the field is algebraically closed really tells us that if we take any semi-simple gadget, so it could be semi-simple, group, could be semi-simple algebra, so on and so forth. Okay, when we represent this semi-simple gadget over K, represented in a vector space over K, then in fact the representation theory should split by as a direct sum of multiples nj of irreducible representations. Okay, where pi j is irreducible representation. Yeah, uniquely up to permutations, irreducible representations. Okay, that's another way to formulate what we are dealing with. Okay, now if in fact you look at the situation of complex numbers, okay. And if you remember also that, you see, when I was considering here this type of stuff, for instance, let's take K to be p-adic numbers. You see, if you take, say, the algebraic closure of p-adic numbers, this is an infinite dimensional space over p-adic numbers. Okay? So there is no good reason whatsoever that one should stick to finite dimensional representation. One has to handle infinite dimensional representations. Okay? If one wants to have any chance to find something non-trivial. Okay? Now, the old work of von Neumann and Murray, in fact, spotted the weakness of the fact that complex numbers would be algebraically closed in the following fact, that if you consider representations over Hilbert space, okay, certainly, Hilbert space, we know Hilbert space, is unique, up to isomorphism and so on. It is really the clear framework for representation theory, infinite dimensional Hilbert space, of course. Then there are such representations. There are representations, of course, of semi-simple objects, of semi-simple gadgets like here, say algebras or groups, algebras, such that there's the following property. Pi, okay, cannot be decomposed cannot be decomposed as a sum pi equals, say, pi 1 plus pi 2, with pi 1 and pi 2 disjoint, with pi 1 disjoint from pi 2. Okay, so I mean, this means that pi wants to be a multiple of irreducible representation. But nevertheless, okay, pi is not a multiple of irreducible. And if it were a multiple of irreducible, what it would mean, if you look at the commutant of pi, you see, if you look at the elements, the operators in Hilbert space, okay, which commute with pi, namely such that pi of a times t is equal to t times pi of a for any a in the group or whatever you are dealing with. Okay, if you look at this set, that should be, if it were a multiple of irreducible, that should be normally isomorphic to an algebra of operators in some other Hilbert space, H1, whatever the dimension. The dimension of that one would be the multiplicity of the representation. But it turns out that it's not isomorphic to this. And it turns out that the fact, though, that it's a multiple, I mean, that it wants to be a multiple of irreducible, namely that it's not decomposable like this, is saying that it is a factor. And saying that it is a factor means that when you look at this commutant, let me call M this commutant. Okay, so this commutant M, being a factor means that the center of M is equal to the complex number, which is exactly like central simple algebras. In fact, central simple algebras were a motivation for Murray and von Neumann. Okay, now, what I'm going to describe briefly is that when you look at these objects, these algebraic objects, namely factors, okay, they do have exactly a structure theory which is modeled on closed subgroups of R plus star, which is sort of God-given, as we shall see, and which will tell us what is the analog of the Frobenius and what is the analog of like the smallest of all factors and of its algebraic closure. Okay, all these pictures will be available. And eventually we shall see that the Abel class space comes from this when we take the field of rational numbers. All right, so let me describe this. But I must say somehow, you know, that I have been working on this theory of factors many, many years ago. In fact, I came here in Ohio State University in 1974 to discuss with Wolfgang Krieger when we were doing this work. But I always had the feeling that it was very related to the book by Bale, but I sort of was unable to, you know, say in more detail what it is. Okay, so how does the theory of factors go? Can I continue here or?
From this side, yeah.
Well, okay, because it's not yet dry. So let me talk just a little bit. First, you shouldn't be afraid by these objects because they are very nice, in the sense that they are just algebras of operators. Okay. Of course, because the object we are dealing with is semi-simple, they are self-adjoint. This means that I use the semi-simplicity, I use the fact that there is an adjoint. Okay? And so if you have an operator T in this algebra, you see if T belongs to M, that implies that T star belongs to M. Okay? I mean, this is really the sort of semi-simple ingredient. Now, it turns out that the first fact, which sort of sets everything going in this theory of factors, the following is that given any factor M, okay, so M, as I explained, is just the commutant of some algebra, or whatever, group or whatever. So I mean, it has certain closure property which is called weakly closed. That doesn't absolutely matter. And that's all. And it's a factor. So it's like a central simple algebra. Its center is a complex number. That's all. That's all we know about it. That's all I want to know about it. Okay? Now there is a completely general first result, which is the theorem, okay, which is the following, which is that any factor M has a God-given time evolution. By God given, I mean it doesn't depend on any choice. And this time evolution, what is it? It's a map, a homomorphism from the real line, to which I call delta. This is in my thesis. So this delta goes from the real line to the group out M. And this group is a group of automorphism classes of M. And it is a quotient of the group of automorphisms of M by the group of inner automorphisms. Of course, you know, anything that will be canonical, you will have to divide by inner automorphisms because the algebra is not commutative. Okay. Now, this map is homomorphism, and it's canonical. So, of course, I mean, it generates a lot of invariants. It generates, in fact, two invariants. The first invariant that it generates was the period set, but I won't talk about it, which is T of M, which is the kernel of delta. But it generates a very other important invariant, which is the spectrum of delta. And that's a closed subgroup of positive real numbers, the star. And there is a nice way to interpret the spectrum, in fact, which is the following, which is to take M, to take the factor M, see, and to take the associated factor, the associated thing, which is M hat, which is the cross product of M by R, where the action of R is by this delta. This cross product is well defined, because if you change the action by inner automorphism, it doesn't change. You see, this is like a semi-direct product. It doesn't change. Okay. Now, on this, one has a dual action. Okay, I mean, this is a structure theory. A dual action of which is of the dual group, and the dual group is R plus star. It turns out that, I mean, it's very important that it's not R, but R plus star. Okay. And this dual action, you can restrict it to the center, because this is not necessarily a factor. So this is the second thing. So if you restrict the dual action, so R plus star action, to the center, Z of M hat, okay, you obtain a flow. You get a flow. Okay, so I mean, the names attached to this are, of course, the name of Tomita, of Takezaki, okay, and myself, because of that. Now, so you get a flow, and now what you can do is the following. You see, there are situations in which this flow is just a trivial flow. This is called type 3.1, in which this flow is a periodic action of some period, and this is called 3 lambda, where the period is 2 pi over, well, the period, I mean, the things which fix it are powers of lambda, lambda to the z. And finally, there is a situation of arbitrary flow. Okay, this is called 3.0, arbitrary non-periodic flow. Okay. Now, the main theorem of classification, to which many names are attached, I mean, the final result, the final case 3.1 was only in 1982 by Agrup, but I mean, many other cases were solved before. So the main theorem, if you want, classification theorem, is that hyperfinite factors of type 3 are classified completely by the corresponding flow, which is the spectrum, if you want, which is the module of the factor. It's called the module of the factor, mod n. Okay, so I mean, it's not a closed subgroup of R plus star, but it's a flow on R plus star. So this is called what is called the virtual subgroup. Sense of Mackey. And Wolfgang Krieger, who was here in this university, contributed in a vital way to this theorem. And moreover, all flows appear. All ergodic flows appear. So it's a one-to-one correspondence. So the simplest case is the case of the trivial flow, which is a flow on a one-point space. Okay, this case of the flow on the one-point space is the factor of type 3-1. Okay. The case of a periodic flow of period 2 pi over log lambda, this is the case 3 lambda. Okay, the case of an arbitrary flow here is called, generically it's called 3-0. And then you have, by the old work of Murray and von Neumann, you have only one factor of type 2-1. You have only one factor of type 2 infinity. This is probably the hardest result I ever proved. Uniqueness of the hyperfinite factor of type 2 infinity. Okay, and then you have only one factor of type 1. One n by matrices and one infinity. So there is this sort of complete classification. And you see now, what happens is that one can make a dictionary and one can understand, in fact, that this unique factor of type 3-1 okay, sits, if you want, I will draw the analogy like this. So consider, for instance, I don't know, Q2. Consider F2. So F2 is sitting in F4. Okay, but I mean F4 is not sitting in F8, for instance. Okay, because 8 is not a power of 4. Okay, so you have this sort of, hierarchical structures of closed subgroups of the module group, which is 2 to the power z. Okay. Now, in exactly the same way, for factors, what you have the smallest one, very surprisingly, is one which at first was considered as the most exotic, namely which is the factor of type 3-1. It's called R infinity. Okay. And then this factor has many extensions, which are factors of type 3 lambda. But again, you see these factors of type 3 lambda, they form a complicated structure because they correspond exactly to the structure of closed subgroups of positive real numbers, and they are all contained in this unique hyperfinite factor of type 2 infinity, and they are all obtained by fixed points. Okay? In other words, you see what you are doing is you are taking the 2 infinity, okay, and it has a canonical group theta lambda, which is scaling the trace, multiplying the trace by this factor of lambda. And then the 3 lambdas and so on are just obtained by fixed points according to subgroups. Okay? And then, for instance, if you consider this extension, it is exactly like a Galois extension. Namely, if you look at this subfactor, it is fixed by a compact group. Okay? There is a compact group that fixes it, and which you can characterize as being unique and being some sort of Galois group. Okay, so you see that there is a very non-trivial theory. Now that theory is based essentially on the following. It's based on one and unique property, which is called the KMS property. Okay, so it's based on the following analysis. Everything is based on the following analysis. Okay. So you see, you take the factor M, okay, and it is sitting in some Hilbert space H. Okay. And now what you do is you simply do the following. You take a vector psi, which belongs to H, and you consider the map which sends x psi to x star psi. In other words, you analyze the involution. I mean, this is the original idea of Tomita. You analyze the involution, but in Hilbert space theoretic way. You fix the vector psi. So psi is like psi 0, if you want. And you vary the x. So this defines an operator which depends on psi. And this operator has a polar decomposition, j psi 0 times delta psi 0 to the power 1/2. And it turns out that, a completely amazing fact is that if you consider the conjugacy by delta psi 0 to the power it, times x delta xi 0 to the power minus it, this sigma t of x still belongs to the algebra M. That means that you don't exit from the algebra by conjugacy by imaginary powers of the module. Okay? And, but of course, this depends on xi 0. And what I proved in my thesis is that if you change xi 0 to xi 1, in fact, this sigma t changes by inner automorphisms. Okay, so in fact, it's completely well-defined and unique. So sigma t xi 1, if you want, is equal to some unitary operator times sigma t xi 0, evaluated somewhere, times ut star. Okay, and this is why you have something which is canonical and doesn't depend on any choice. So from there, the theory evolves. And I mean, it turns out this KMS property, the following is that you can abstractly understand what is the relation between sigma t, this time evolution, you see, which are automorphisms of M, and a priori they depend on the vector, but rather on the state, which is defined by phi of x, which is just evaluation of the vector. Okay, and you can understand the relation between this evolution and the state just as the difference between left and right, namely by the following property, which I shall use later. This is why I want to mention it. Well, maybe let me write it here because it's not so. I want to use it later. So this property is the following. So the relation between phi and sigma t phi is a KMS property. KMS relation. Now this KMS relation is the following: is that so it's an abstract relation between a one-parameter group of automorphism and the state, and it says that for any element x, y, which belong to M, there exists an holomorphic function f of x, y of z, of the variable z, where the imaginary part of z is in the interval 0, 1. So if you want, we are dealing with the strip of imaginary parts between 0 and 1. And so the rest is excluded. So all that is excluded. And that function should exist and be such that when you take its boundary value f of x, y at the point t, this is equal to phi of sigma t of x times y, whereas when you consider the boundary values f of x, y at I plus t, okay, this should be equal to the same thing, but with the order of the elements reversed. Phi of y sigma t of x. Okay? So in a sense, if you want, it's some sort of fundamental analysis of what is a simple central algebra, but now no longer of finite dimensions, but of infinite dimensions. And it turns out that this analysis gives us all the ingredients that were missing for the Archimedean place. Namely, now we have these many examples which correspond to closed subgroups of positive reals, and so on and so forth. Okay, so now the landscape is open and full of interesting stuff. Okay. Now, so now let me explain how this is hidden behind the Adel class space. Okay, in the case, so I will only consider the case of rational numbers now, and I will explain how all this led to the Adel class space. So I will start with an extremely simple observation. So let me not blush about this observation, even though simple it is. Okay. You see, we all know one thing. We all know one thing that Dirac found, which is a wonderful observation of Dirac, and which I sort of alluded to last time. And this observation of Dirac is what is a characterization of operators whose spectrum is a set of integers. Okay? You see? I mean, I'm asking something very, very simple. I'm asking what are the operators T, so that the spectrum of T is equal to 0, 1, 2, and so on, with multiplicity 1. Okay, I mean, this was very important in quantum mechanics, because you wanted to quantize, and quantize was replacing the fact that you have an integer by the spectrum of an operator. And you should know why conceptually. Okay? Now, the reason that Dirac found is the following, is that T should be of the form T equals A star A, where A star minus A star A is equal to 1. Okay, and this is what set forth quantum field theory, because if you have that, then you can write what is the quantum field associated to the electromagnetic field. Okay, you just replace everywhere where you would like to have the absolute value square to quantize, you replace it by A star A. Okay, and it is quantized automatically. But you see, I mean, I'm just alluding to the following fact, that this point, very simple point. First, let me prove it. As simple as it is, let me prove it.
Same operators you used before.
Yeah. It is the one I used last time. That's why I was mentioning it. Okay? But I used it concretely, but let me prove it abstractly. Okay? Imagine that you give me an operator of this form. Okay? Let me prove to you that its spectrum is necessarily the set of integers. Okay? So you see, first of all, the operator is of the form A star A, so it's positive. So spectrum is positive. Self-adjoint and positive. So I can start and look whether this is in the spectrum. And this is 0. Okay? So let's start something which is in the spectrum. Now what do we know? We know from elementary considerations that the non-zero part of the spectrum of AB, this is the non-zero part, is equal to the non-zero part of the spectrum of BA. I mean, this is a child play. Okay? So what do we know? We know that the non-zero part of the spectrum of A star A, okay, is equal to the non-zero part of the spectrum of the other one. But so they differ by 1, so you can shift by 1. Okay? So I mean, if you have E, you also have E minus 1. Okay? Provided E minus 1 is not 0. If it were 0, you couldn't conclude that you have, because it's a non-zero part. Okay, so imagine that I have not an integer. Imagine I start with something like pi, for instance. Okay? Then you see, I never meet 0. But then I get negative numbers, and this is contradictory, because I have something of the form A star A. So the spectrum is only formed of integers, and it's very easy to see that you get all integers. Okay? So, I mean, this is, completely simple fact, which allows you to understand what it means to have spectrum, the integers. But now let's be much more crazy, okay? And let's ask the following question. What are the operators T? So, I mean, don't be frightened, okay? So that spectrum of T is a set of prime numbers. Okay, namely 2, 3, 5, 7, 11, 13. Okay. And I mean, this question is sort of important, you see, because if we are going to get anywhere with these prime numbers, we have to know that it's a problem which is logically well formulated, that we encapsulate it all. That, if somebody comes up and finds a new prime number, we are not going to say, oh, wow, I have to redo something again, and so on. I mean, we have to capture it all in one stroke. Okay? Now, it turns out that this is beautifully simple answer, but extremely suggestive. Okay? And it is the following theorem. And let me attribute it to Euclid, okay? Because that's really... I mean, he didn't quite write it like that, but I mean, the essence of what he said. Okay, so you see, we want to understand this. I mean, this is a subset of real numbers, of course. Positive real numbers. Now, if you think about it, you'll find that it's really due to Euclid's theorem, okay? So the theorem is the following, is that spec T is equal to this. That's equivalent, in fact, to saying that the spectrum of S of T is a set of positive integers, n, where what is S? S is a symmetric functor. Okay, namely it's the functor which replaces space by the sum of its symmetric powers, namely S of a space H is a direct sum from n equals 1 to infinity of the nth symmetric power of H. And of course it's a functor. You see, if you have an operator, of course this operator will act on the corresponding space. Now just think about it for a while, okay, and you'll find that this theorem is true actually, okay, but this theorem tells you a lot. See, in spite of its simplicity, it tells you a lot, because it tells you that there is one way to think about prime numbers, and that way is, you see, to not think about the original operator T, but think about S of T, okay? Then the spectrum is very simple, it is integers. But then you have to remember that you have applied this functor S. So you have to encode in your system the fact that you have applied this functor S. This functor S is what physicists call second quantization, bosonic second quantization. Okay? So you have to remember that you have the functor S. And how do you encode that? Well, you encode that by an algebra now. So now we shall be back to the type 3 and so on. Okay? So namely, you see, now you work in that space, S of H, and you work with an operator which is like the Dirac A star A. Okay? But you want to remember that your space came by this second quantization functor. In fact, there is a corresponding algebra, and with a little thought, you find out that this algebra is the following. It is the Eck algebra. It is the algebra, say, related to creation and annihilation operator. And it is the Eck algebra, so let me describe this. I mean, and then we really go into the interesting stuff now. Okay, so what is this algebra? Okay, you see, first of all, what is the Eck algebra in general? So if we take a discrete group, gamma, so gamma is a discrete group. When we take a discrete group, we have very simple things associated to the discrete group, like the regular representation, L2 of gamma, and the regular representation of the group, which is just how the group acts in little L2. And I mean, if you look at discrete groups and so on, you'll find out that the regular representation of a discrete group in general is of type 2-1. So it's not type 3. It's not the interesting thing that we want. Okay? However, imagine that you have a discrete group gamma, and you have a subgroup, gamma 0, in gamma, but which is not normal. So it's not a normal subgroup, but almost normal. And the algebra we are dealing with will come from that. Almost normal. So what I mean by almost normal, you see, the group would be normal if, when you look at gamma acting on gamma mod gamma 0, the orbits would just be a single point. Sorry, a gamma 0 acting on gamma mod gamma 0. Okay? The orbits would just be a single point. So now we ask that the orbits are finite. Okay? And in fact, if these orbits are finite, they will have a length. And these lengths I will call L of G. So this is the length of the orbit. Okay, of the orbit of gamma 0, of the trivial point. You see, I am saying that take discrete groups, okay? Take a subgroup. And now, look at the left action of gamma 0 on gamma quotiented on the right. If the group were normal, it wouldn't move anything. But now I am saying that it's almost normal when it moves very little. Okay, just a finite amount. Now this is what happens when you consider for instance GL2Q and GL2Z. Okay, I mean, if you consider as a group gamma, the group GL2Q, the gamma equals GL2Q, and if you take gamma 0 equals GL2Z, then you get this situation, and this is how you get the Eck operators, essentially. Okay, I mean, this, if you want, Eck algebra is related to what one calls the Eck operator. Now it turns out that if you follow the very simple route which comes from here, you get something which is slightly different. You don't get GL2, but you get PQ, P of Q, if you want, or P sub Q rather, where P is a parabolic subgroup. Namely, P is an algebraic group. It's an abstract functor, if you want. And it is the algebraic group which is the AX plus B group. AX plus B. In other words, it is matrices. I mean, this is not writing it as an algebraic group, it doesn't matter. Matrices of the form 1AB. Okay? If I wanted to write it as an algebraic group, I would have to put A inverse, so that I impose elements to be vertical. So it's the group of 2x2 matrices of this form. This group looks very trivial, but believe me, it's not trivial. I mean, I gave, for instance, a little proof of Morley's theorem using this group It's a group which has a lot of hidden structure because it uses both addition and multiplication. So in a sense, if you want, even though it's just a group, it embodies in its structure both the addition and multiplication, so it really contains the ring structure of what you are dealing with. Okay. Now, if you take this group now, it turns out that exactly as for GL2Q and GL2Z, you have a subgroup, which is the group P sub Z, okay, and which is now almost normal also. So P sub Z is almost normal in PQ. Okay, and now let me write the theorem. See, so now PZ is this algebraic group applied to the ring of the integers.
All the integer guys.
Okay. You see, so in other words, so A is plus or minus 1 and B is an integer. Okay? So I just apply the same functor to the ring Z. Okay? Now, so now I will write the theorem, which show you the relation with class field theory, type 3 factors, and so on. And the thing is the following. See, exactly as when you have a discrete group, you have the regular representation. Now, if you have a pair of groups like this, there is a regular representation also, because you can consider the action of PQ, I mean of gamma, acting on the Hilbert space, which is little L2, not of gamma, of course, because it would be the same as for the discrete group, but of gamma mod gamma 0. Okay? That's gamma is acting there. Okay? Now, the commutant of gamma is generated by the Ecke algebra. Namely, it's generated by the following algebra, where an element here is just a function f, okay, f of g if you want, where g belongs to gamma, but it's bi-invariant. So the function is constant on classes, double classes, okay? And the convolution in the Ecke algebra is the same as what you would imagine, namely you take f1 star f2, and you evaluate it on a double class G, and it is simply given by sum of f1 of G1, f2 of G1 inverse G, but you have to be a bit careful because you cannot sum over all of gamma here. That would be too repetitive. You have to sum on gamma mod gamma 0. Okay? On the right. So it's a nice algebra, it has an involution and so on. Okay, it's the Ecke algebra. And it generates a commutant of the action of gamma. And moreover, you see, it has a completely natural, exactly as for the regular representation, you have a completely natural vector, which is the vector 1 here. Okay, so you have this vector psi 0, you can take the vector which is 1 gamma 0. Okay. Fine, so now let me write the theorem, which I won't prove, of course, it's just motivation. And I will only treat the case of Q, of rational numbers. In fact, I do not know of any good generalization of this theorem for arbitrary number fields. As you will see, this is very strange. But I do not know of a good generalization. No, I mean, these are not generalizations that I want. These are generalizations, but they are not the generalization I want. Okay, so the theorem is the following. So it's a theorem which is in a joint paper by Jean-Benoît Bost and myself. And the theorem says the following, you see. Okay, so first of all, what you see immediately is that when you look at this space, gamma mod gamma 0, where gamma is PQ, when you look at the set PQ over PZ, okay, you find out that PQ over PZ, this is a very simple remark, in fact is equal to the restricted product of the trees T sub P over all prime numbers where T sub P is a tree of SL2QP, in the sense of Serre's book. Okay, so if you want the quotient of the X plus B group by this subgroup, it's a simplicial complex of infinite dimension, and it is a set of vertices of this. Okay, how do you see that somehow? You see, what you do, you take the finite adels, A sub F, okay, and you take the corresponding group P for finite adels. Okay, now you know that the product of trees is acted upon by the restricted product of the SL2QP. So it is acted upon by the restricted product of this. Okay? And you will immediately find out that the isotropy is the restricted product of P sub R, F, if you want, where this is the maximal compact subring. Okay, this is very easy to do. And it's very easy to see that these subgroups are transitive on the corresponding trees. You see, this corresponds to the fact that the X plus B group is transitive on the Poincaré disk. But the Poincaré disk is a homogeneous space over the X plus B group. So you have this action. Okay, you have this action. And from this, you see that this space gamma mod gamma 0 is in fact equal to this. And what it means really is that when you look at the action of PQ on this space, and at its commutant, which is the Eck algebra, in fact, this action extends to something which is bigger, and it extends to the action of P A sub F, which normalizes everything. And I mean, when you look, say, modulo inner, if you want, you find that you have to divide by the closure of PQ inside P A sub F. And that gives you, in fact, exactly the group CQ1, namely the group of ideal classes of modulus 1. So, in fact, the first thing that we find is that there is a canonical action on the Eck algebra, which comes just from this. There is a canonical action of this PQ, of this CQ1, namely those ideals classes, J belongs to CQ, such that modulus of J is equal to 1, on the Eck algebra H of PQ and PZ. Okay? So there is a completely canonical action of this group. Okay, the second fact is the following. The second fact is that you can identify the, what is called the modular automorphism group. So if you want the algebra, the H in L2 of gamma mod gamma 0, okay, generates a factor of type 3(1). I have to finish the statement of the theorem. Okay, generates a factor of type 3(1) whose modular automorphism group, namely with sigma T phi for the particular state corresponding to psi 0, sigma T psi 0, is given by, you see, when you apply it to the class function, to F, and you evaluate on G, this will be given by the length that I defined before, which is an integer, divided by the length of the inverse of G to the power IT multiplied by F of G. Okay, that's a very simple fact, so you identify it. But it's a one-parameter group of automorphism of the algebra. Fine. Now the third fact is that for any beta, okay. No, so if you now look at a constant beta, which is in positive real numbers, beta positive, okay, and you look at the set K sub beta, which is the set of states phi on the Eck algebra, which satisfy the KMS condition, but with the parameter beta, where this means that simply here, instead of taking 1, I take beta here. Okay? So and this is the notation in statistical mechanics. So if you look at the state satisfying the KMS beta condition for sigma T, okay, then you find the following amazing picture, that when the beta is called the inverse temperature in physics. So if you look at beta equals 1, you have only one such state. Okay? But as soon as beta gets bigger, namely the temperature is cooled down, what you find is that the set of such states is a showcase simplex. Okay, so it has extreme points. It's a showcase simplex. So every point is unique combination of extreme points. And the extreme points are parametrized by the embeddings of the cyclotomic extension of Q in the complex numbers. Okay, they are exactly in one-to-one correspondence with the embeddings. Okay, and now the beauty is the following: is that if you go all the way to beta equals infinity, okay, namely instead of requiring the KNS condition for such a strip, you require it for all the upper half space. These are called zero temperature states or vacuum states. Okay, then the same is true, and now you get the class field theory isomorphism, namely third. You see, namely the global class field theory isomorphism is obtained like this. Isomorphism is obtained like this. This is the most important. The rest you can forget. It's obtained like this. Okay? So you take this infinite temperature, zero temperature state. Okay? You take the extreme ones. So take one, call it phi. Okay? Now, you can take this state, and the algebra, the AK algebra, could be defined over rational numbers, namely with rational numbers coefficients. So you can consider phi and apply it to H over Q, the rational points of H. Okay? Now, this will be a subset of complex numbers. Okay? And the state will be uniquely defined by density of the rational points, by its restriction here. But now what you can do, you can take a Galois group automorphism of C and act there. Okay, so you can take sigma, which belongs to the Galois group of C over Q, and you can consider the composition of the state sigma composed with phi. This makes good sense. You see, I just apply. It's very non-trivial that it's a new state, of course. Now the theorem is that it is a new state, and this state is of the form phi composed with ρ, where ρ is a unique element of CQ1. Unique element of CQ1. And that's a class field theory, global isomorphism. Okay? Explicit reciprocity. Okay? Global, not local. Now, I don't know how to do that for other algebraic number fields. Okay? And of course, it should be hard because somehow, you know, this, here I am using the fact that we know what this is for the case of rational numbers. But now let me write the fifth statement, and this is where the Adel class space enters. You see, we have a factor of type 3-1, which is this. So now we know that there is a corresponding type 2, which is like the algebraic closure, and we know what is a Frobenius. Okay? So we can compute it. So compute the corresponding type 2. Compute, I called it M hat. Okay, the corresponding type 2 infinity. And what do you find? You find that this is non-commutative space, of course, in the sense that you have non-commutative algebra. And it corresponds to a non-commutative space. And what is this space? It's exactly the space of Adel classes, A over K cross, which is type 2 infinity. So that's how I got to the space. And that's how I got to what is the group which is acting on the space. Because on that space, you not only have now an action of CK1, namely of the things which are of modulus 1, but of all Adel classes, which is the Adel class group. So the correspondence, of course, is via the cross product. Okay? Namely, it's via the main recipe of non-commutative geometry, which is that the quotient space should not be viewed as quotient, but should be viewed through the semi-direct product, the cross product algebra. Okay, so I mean, I just wanted to mention that so that you can see what is the origin of the stuff. And the origin of the stuff is that I believe that there is a not totally uncovered, very important local class field theory for the Archimedean places, which is very non-trivial, okay? But it gives a lot of ground to understanding what the Frobenius is. Now we shall forget all this. This is why I did it at the speed of light, okay? So you don't have to worry about it. But, yes? Sorry?
The motivation for this is non-commutative geometry.
Yeah, exactly. So this is where non-commutative geometry is behind the scene. Of course, you see, what we shall see is the spectral realization and so on. Then we shall have to fight with true problems, which are problems of analysis, and we can forget all that. But I mean, okay, this is the motivation. Sorry?
Why isn't